In this presentation, we will start from the most basic Markov chain and then extend it to Markov decision process, and then further extend it to multi-agent Markov decision process, which will involve some concept from game theory. So we'll introduce the model and also some algorithm to solve it. So first, I start with the Markov chain. Markov chain have these three parts: the stage, states, and transition probability. So if you take an example of the weather transition, we see the stage will be the day 1, day 2 to some day t. And we will consider this t to be either finite or infinite. So the state as t for this example have three states. Can either be cloudy, raining, or sunny. And the transition probability is saying like if today is cloudy, I know that tomorrow will be sunny with probability 40%, and tomorrow will be raining for 30%, 50%, and it will still be cloudy for 10%. And we call it Markov because the transition probability is only related to the current state. It doesn't relate it to all the previous stage. So Markov chain has a large application in a lot of area, but there's one shortage. That is like we know all this transition probability. We can analyze or predict what the probability of tomorrow is sunny, but there's nothing that we can do about it. So we can make the first extension that introduces an action. So saying that when you take different actions, you will have different transition probabilities and also get different reward. So this reward will be a performance index tells you how good the action will be. And this reward is related to the state S and the action A. It means like what is the current state you are in and what action you are take. You will have different reward. And after we introduce this action, we want to know what is the best action we should take. So our objective will be find a policy. So this policy means that this policy is a mapping or a function from the state to action. So it means that facing different states, I should be able to know what action that I should take. For example, today is sunny, then I didn't need to bring an umbrella, something like that. So basically, the table tells you what to do when you face different states. And our objective is to find this policy so that we can maximize the expected accumulated utilities. So the first part is this sum over t. So we see that we are sum of the reward from the current state to the future t. So the benefit of this is that we are not myopically consider the immediate reward we are getting today, but also considering all the possible future reward we will be getting. And this beta is the discounted factor. It's a number between 0 to 1. So an example for this is that if you have a choice to get $1 today or get $1 10 days later, which choice you would choose? You will certainly choose to get $1 today, right? Because if you get $1, you can put it in the bank and there will be interest, although maybe neglectable. So this discounted factor is showing you that $1 in 10 days later is less than $1 in today. And also out here, we see that the reward is a function of state and action. And because the action is just the outcome of this mapping, so we can replace the action as the phi s. And we have the expectation here because this is a dynamic and probabilistic model. So we have a transition probability. All the future states is not deterministic. That's why we need to take expectation over all the future states. And what I want to say is that MDP is also related to some hot topics right now, like the reinforcement learning, which is model free. So basically saying like in reality, we may not know the exact form of this transition probability and the reward. So what we do is that we take actions, interact with the environment, and then get some information of what the reward is and what the state is. So by doing this iteratively, we can learn what is the best action or the best policy we should make. So we have shown that the MDP model, and also this is our objective function, which is related to the initial state as T0. T0 is the initial time, initial stage, as T0 is the initial states, and defines the policy. So if we fix this, this is fixed. So this is a function of this two. And as we said, we want to optimal this. So it's optimal over all of possible policy phi and get the optimal policy phi star. And after you get phi star, this function will be just a function of the initial state. And we call this the value function, or the optimal cost to go starting from the initial state as T0. So there's no relationship with the phi for the value function because it's already optimal. And then we use dynamic programming, which applied the optimality principle. So what this means, I can give you, it means that if I have an optimal path starting from here to here, like shown in red, then starting at any point on this equilibrium path, on this optimal path, I should still achieve optimal starting from this point to the end. So that gives us a way to divide the complex problem into some sub-problems so that I can conquer them one by one. So it may not be so clear. So there's a simple example of a network, and you want to find the shortest path from this start point to this end point. And the number of these links are the lengths. So you see that for here, we are automatically considering accumulated reward because it's a summation of all the lengths here will be our final long-term objective, which is the shortest path from here to here. And also because it's finite state transition, there's no discounted factor, and the transition is all deterministics. So if you directly go here to here, the most easiest way to think is just to brute forcefully list all the possible way, like here, 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 here. But this can be really complicated if you have a large network. So what we should do is that first we consider this sub-problem here. Suppose you have successfully arrived at this node. What action you should take? You should take this, right? Because there's no other choices. And you will get a value function or optimal cost to go starting from this point of 2, right? And if you start from this node, you'll get 3, and this is the optimal path. If you start at this point, you get 4, and this is the optimal path. So now you can go one step backwards to consider if I have arrived at this node, which path should I take? I have 2 choices here, right? So if I choose 5, and then I will arrive at 2, so I will get 7 in total. If I choose 3, I will get 3. in the future. So I get 6 in total. So which one should I take? I should take this and get an optimal cost to go of 6 from this stage, or we say the value function is 6. If you start from this node, it's obviously you should choose this and get value function of 6. If you start from this node, you will choose this to get the immediate cost of 5, to get a value function of 5. So now you can go one step back and see the value function is 7, 8, 9 for these 3 nodes. And finally here, you will see that what is the best policy, just here, and go to 8, and you get 9 in total. So the shortest path from here to here will be 9, and then you will know the optimal path, what the optimal path is. So note that if you myopically just considering the immediate cost, you may arrive here. You may not be arrived at this long-term optimal. And also you see that there is some redundancy that we compute the value function starting from every nodes. So suppose that you make a mistake at some point and deviate from this optimal path. Suppose like you arrive at here, you still know what you should do so that you can compensate for your mistakes. I mean, you can still achieve optimal starting from this point to your goal. So in our case, we have infinite horizon, and there's transition probabilities, discounted factors. So we will write the Bellman equation as here. So which means that you're currently at ST, and you take an action. You want to find the best action. So when you take different action, you will get different immediate cost, and also it will affect your expected future cost, because it will affect where you will go for the next stage. And starting from the next stage, you will have a value function or the optimal cost to go. So the right hand side will equal to the left hand side, which is the optimal cost to go starting from ST is equal to the current reward and the future reward. And it should be true for all the ST and T. So you see that there's a value function here, value function here. So basically you are trying to find the equilibrium point. You will try to find a fixed point of this function. So there's many ways to solve this Bellman equation. You can use value iteration or policy iteration. But here we say that we can also use linear programming to solve this. So first, there's a max of A here. So basically what we want to do is that we want to find the equality. So what we do is that we make a constraint. This V is bigger than this guy, and then we try to minimize this V so that at the optimal of this linear programming, we are actually achieve the equality here. So we get rid of this max because it's bigger than the max of A, so it should be bigger than all the possible A. And this alpha is any positive weight, and this weight will not affect the optimal point and optimal value as shows in this paper. So I will show you in 2D. So if we have only two-dimension states, two states, 1 or 2, then you see that we can plot V1 and V2 here, and the feasible reason of this constraint will be this. And you want to minimize this objective, which is a line, and you find the minimum you can achieve is this point. And if you change the alpha, you're just changing the angle of this line. But as long as positive, you will always hit this point. So you have the same optimal. So finally, we can extend MDP to multi-agent MDP, and because you have multi-players, you have to use the concept of equilibrium from the game series. So this extension is also straightforward. Previously, it's controlled by one player. So now we say that n player will control the transition probability P. And also, the reward for each player I will depends on the global state S and also all the action of the players. And similarly, we will assume each player is selfish but rational. So what they do is try to find a policy that can maximize his own long-term utility. So this is his policy is a mapping from the state to his own action, which says that I observe the state, what action should I take? And for the Nash equilibrium, everybody will take the action, will not be able to observe others' actions, or you can think that they take their action all in this simultaneously. But things are not that simple because we have one player. Our solution concept is just optimality. But now you cannot know or persuade others to cooperate with you so that you get your maximum utility. Especially in the cybersecurity setting, when we have natural confrontation of defender and attacker. So now we have multiple agents. What the solution concept you should consider is the equilibrium. So the equilibrium says like if everybody remain the same at the remain the same policy at the equilibrium, then if you deviate from the equilibrium, you cannot get any benefit. So then nobody want to change their policy at the equilibrium. That's why it's called equilibrium. And graphically, if you have two players and a zero sum, which means that R1 plus R2 equal to 0 or some constant, then both players want to maximum their utility. So for player 2, maximize R2 is equal to minimize R1. So now if you plot R1, one player want to maximum and the other guy want to minimize it. So you see that there's two policy here. If I remain the same and you change, you find you getting worse because you want to minimize but you are getting larger. If I remain the same and you change your policy, you see that you are also get worse because you want to maximum the policy but acting you are getting small number. And for our case, we consider in general sum game, so we cannot show you in the figure, but you get an idea of the equilibrium. So now we will do some extension to our previous setting. First, the action side can be state dependent. For example, at state 1, you have 2 actions. At state 2, you have 3 actions. And this action can be totally different. So the action you can take depends on which state you are in. And also, when you consider multi-agent, you can extend the pure policy to mixed strategy. What would this mean? So previously you have 3 actions, and your pure policy is just to choose action 1 or action 2 or action 3. So now what you do, the mixed strategy is that you choose action 1 with a probability P1, choose action 2 with probability to P2, choose action 3 with probability P3. So P1, P2, P3 will be bigger than 0 and their summation will be 1. So this is called a mixed strategy because it's a mix of all the P policy. And the P policy is a special case of mixed strategy, because if P1 equal to 1, it's become a P policy. So why will we introduce the mixed strategy in the multi-agent setting? The reason is simple. Let's say you are playing a rock paper scissors game with the other guy. So if you choose the P policy, suppose you choose stone, then the other guy will choose paper, right? And then you do not want to choose stone, you want to choose scissors. And then the other guy will want to choose stone. So you see that you will never settle down. So this is not equilibrium. But if both players will choose each action with probability 1/3, then you see that you are actually settled down. You will not change your policy. Actually, this is what you do in real life. You are automatically adopt this policy that randomly choose these 3 options. And one more thing is that the policy is different from the action, because here your policy is to choose each action with some probability. But action is just the realization of your policy, because each time you can only choose a paper or stone or scissors according to this probability. So finally, when we introduce the epsilon-Nash equilibrium, as we have said, if for this general sum you have 2 reward, U1 or U2. This is the long-term reward, and we have 2 person, 1, 2. So suppose first the epsilon equal to 0, it becomes the Nash equilibrium. So which says at the equilibrium, if player 1 deviate from this equilibrium policy and the other guy didn't change, then he receive a loss in his utility, U1. On the other hand, if U2 deviate from the equilibrium policy, then he receives also a loss to his own utility U2. And because Nash equilibrium may not always exist, we introduce this epsilon as a realization to the Nash equilibrium. So yeah. So compared to the MDP, which we can solve by dynamic programming and further solve it by linear programming, we show that our multi-agent MDP is also equivalent to mathematical programming, although this time it is nonlinear. So we have this theorem. First good thing is that there exists at least one Nash equilibrium for our general sum stochastic game. And the second thing is that the multi-agent MDP is equivalent to this mathematical programming, and which means the optimal here is the global optimal of this nonlinear programming will be the Nash equilibrium points. And also at equilibrium, this objective function will achieve 0. And the number 3 tells you that if when you do the optimization, if the objective function you didn't get a 0 but some gamma, then there is a relationship between the gamma and the epsilon. So the larger epsilon, the larger gamma is, the larger epsilon is, which means that you give more realization for these problems. But it's also give you some realization about this about program, because for this nonlinear programming you may not always find the global optimal. You can stuck at the local optimal, and this is the performance index tells you how good the programming works.